neural networks, the cool stuff, and here's where it gets pretty abstract, and I hope you guys stay with me here. But essentially what it does is it tries to mimic how we think our brains work. You know, the nerve ending connected to your stomach fires because your stomach's empty. It connects to a neuron in your brain, and then it fires off that neuron fires off other neurons, and it just cascades through your brain until you have this complex thought of, man, I want a hamburger. And essentially, neural networks, like at least the machine learning model of a neural network, is made up of 3 different types of layers, and they're all interconnected from the previous layer. You have your input layer, your hidden layer, and your output layer. You can see this is a neural network that's trying to guess the final price of a house based on the bedrooms, square feet, and this neighborhood ID. And every connection from the previous layer, or every node from the previous layer, is connected to the node of the next layer. And all a node is it just holds a value. In this case, this node is currently holding 3, this one's holding 2,000, that one's holding 1. All it does is hold a value. And all a weight is a value that you multiply the previous node by to put into the following node. So let's say that our neural network model was just these 2 nodes, just a 2-node neural network model with just an input and output node hidden layer. And let's say our weight was 1 here for this connection. Your value for your temp value would just be a 3. Your output would be a 3 in that case. So this is what's called a fully connected neural network. Every node in the previous layer is connected to every node in the following layer. And these weights, an important thing to think about these weights, is they can be positive, they can be negative, or more importantly, they can be 0. So this node cannot be affected by this one because the weight can be 0, and thus it's only based on these 2 nodes. And that's sort of an important understanding, especially as we get into deep neural networks. But yeah, this would be the equation for calculating your temp value based on this. It's just bedrooms times the weight that connects that bedroom to that temp 1, square feet times the weight or the weight of the connection between square feet and that temp node, and also neighborhood, same thing. And this bias we can ignore for now, but just know that basically what a bias does is the value that you add to this function, I guess, to basically turn on or turn off a node. Like let's say you have a noisy node that keeps like messing up your data. You use your bias to turn that node off. You give it some negative value. And also there's something, and we're not going to go too far into this, but there's something called an activation function. And there's sort of 3 different main types. One's a threshold function, and it looks a little bit like this. Let's say if your value is greater than 0.5, give me a 1. If not, give me a 0. You have a sigmoid function, which is something like this. So high values are a 1, low values are a -1. And anything in between is some value based on the sigmoid function. And what we also have is a ReLU function. And what that looks like is this. Let's say this is our y-axis. Oh shit, I drew that wrong. Y-axis over here. So any negative value will just be a 0, and any positive value will just be the positive value. So -20 will be 0, 30 will be 30. That's essentially what that is. And what you do if you're using activation functions is you would plug this temp value 1 into the activation function, and that would be the actual value that was stored in that node. Now, neural networks can classify or predict based on how you set them up. And feed forward versus back propagating. All I mean when I say feed forward is just feeding data through this model. So you evaluate what your temp 1 is going to be, your temp 2, your temp 3, and then you evaluate what your final price is going to be based on those values. It's fairly simple. You just feed it through a simple, fairly linear equation in this point. And one sort of notable thing when I look at this, at least, I noticed that let's say we didn't have these 2 variables, and again, it was just a 2-node neural network with an input and output node. And therefore, for our equation for output, we wouldn't have this neighborhood or this square footage. So it would just be temp value 1 equals bedrooms times weight plus bias. I don't know if anyone has noticed, but that's sort of really similar to the y equals mx plus b from linear regression. So essentially, this is like a bunch of linear regression functions sort of added together and stacked on top of each other, is essentially what a neural network is. And how you optimize a neural network is via gradient descent. And what gradient descent is for this output, to train the network, we give it our features or our input, and then we compare the output to what we expect the output to be, and then we adjust our weights accordingly. We adjust our weights to bring that final price estimate to what the value actually should be for that data. And we do that via gradient descent. Essentially, we take a simple calculus. I'm not going to go into it, though, with you guys. If you guys want to know, you can come talk to me after this, and I'll walk you through gradient descent. But essentially, you can imagine it as, here, I'll draw us a little example here. So let's say this is our error, and error is synonymous with loss, so I'm just going to say E/L, and our weight for a single weight. Let's say this is weight 0, 0, so the weight that's associated between the bedroom and the temp value 1. There's going to be some mapping that's going to look kind of like this for our error based on that weight. And what we do is all these weights are assigned randomly in the beginning. It's just completely random numbers. So let's say we just randomly end up there. What we do is we take the derivative based on that weight, and what that gives us is sort of a direction of which way is down for error. And we take a step in that direction with the weight. Then we try it again. We take another step. We take a step there. We take another derivative. Take another step in gradient descent until we get to a minimum, and our derivative equals 0. And what we call that is a local minimum. And the reason we call it local minimum is because the reality is much more complex than this simple little curve. Oftentimes, you'll look more sort of like this, and you'll have these local minimums. And you start off at a random point, and all it can do is step downwards until it reaches this pit. And once it reaches there, it has no way of knowing that there's a deeper pit somewhere else. You can imagine it as like the common sort of antidote is imagine you're standing on the side of a mountain in deep fog, and all you can see is the ground beneath you, and you're trying to find water. All you can do is go downwards, and you have no way of knowing that, you know, across the other mountain there's a deeper valley. You just know you're trying to go down, essentially. So that's what gradient descent is, and we're going to talk about at the end, we're going to discuss another method of optimizing a neural network. But for now, and this is most typically how you do it, we're going to stick with gradient descent.
Hey, Josh, what is backpropagation? You talk about before backpropagation.
Yeah, backpropagating is when you use gradient descent to optimize your network, to change those weights and optimize your network. Sorry, I probably should have made that more clear. Does that make sense to everyone? And also, like, this is the most abstract concept we've gone through yet, so please ask questions. Yes?
Can you just, at a high level, one more time, explain the difference between feed-forward and back?
Yeah, feed-forward is when you give it input data and you let it evaluate. It basically pushes through and evaluates this node, this node, this node, and then it finally evaluates its guess of the final price in this case. So it's when you use the neural network. And backpropagation is when you correct for its error, essentially. So anytime you utilize a neural network, you're feeding forward through that network.
Feed-forward might have like a bunch of different layers, but it always goes through that number, whereas the backpropagate might go through an indeterminate number of times repeating the same layer?
Yes, kind of. Basically, just for all intents and purposes, feeding forward is just when you run data through your network, and backpropagation is when you go back through and you adjust those weights
So you
to
might use
optimize.
both at the same time. Like you might have multiple layers and then backpropagate.
Well, exactly. What you do is you feed forward, and then you compare the output of the neural network to what it actually should be, and then you backpropagate. So you feed forward, then you backpropagate. Feed forward, then you backpropagate. And via that, and comparing, and each time comparing to what the output value should be for that input data, this is during the training process, you optimize your network. Does that make sense? Yes.
Yeah, how do you prevent getting stuck in your local minima? Is that just having enough like random initial guesses?
Well, yes, kind of. What you do is you just restart the whole process. You restart, and thus you're, let's imagine something like this, and you started here the first time, you restart and it randomizes your value, and now you're over here where the actual, when you go down, you'll hit that deepest valley. So essentially you retry the model from scratch, And that's where something like pickling becomes really useful, because you can save off your best model and then run it again, save off your model if it performs better, and so on. Any more questions? I encourage them. I think we're doing pretty decent on time. All right, deep neural networks. Whenever anyone says deep learning or deep neural network, all they mean is there's multiple hidden layers. And multiple hidden layers, basically they're used for complex, sort of non-linear problems. And there's several different types of deep neural networks. Fully connected, which is what we've sort of gone through already, where every node in the previous layer is connected to every node in the next layer. And there's convolutional, which we'll just go over in a minute, and also you can apply deconvolution. There's also something called a recurrent neural network. We'll talk about that at the very end. But yeah, I want to use this example to sort of get you to understand how this might actually work for something like handwritten digit recognition. So let's say this is our input data, and our output is simply, for that, a 7, for that, an 8, that sort of thing. An optimized network, a network that's already fed forward and back propagated, enough to optimize the network to accurately classify. What you imagine this first layer, first hidden layer would look like is the weights for most of your input would be every pixel in this image. It would start from, let's say, the top left, go down each row, concatenating each time until you get this huge array of every single one of your pixels in that. And you can imagine that that's, your input data of, let's say 2,500 pixels or something like that. And your first layer of hidden nodes would look something like this, where if you mapped out which connections or which weights connected to it had positive values, and which weights were 0, you get something like this. So for all these pixels, let's say this is this first node of your first hidden layer, and every pixel here is white because the weight connected to that pixel is 0, so it's not affected by that 0. Whereas the black area here is where the weight is 1. So this node gets activated when this region has high number of pixels inside of it. Does that make sense? And then what this second layer is, it's a combination of those first layers. The same way that this first layer is a combination of those pixels, this is a combination of those activated nodes. So let's say you had one of these nodes that represented this, you had one of these nodes that represented, this, like a circle in the lower region. Then this is sort of how your end would look like that. Let me back step a little bit. Let's say you had a region that was high activation here in your first hidden layer. You had a region that was high activated here in your first layer, and you had a region that was high activated for like a line on the right side. Then your second hidden layer might be a combination of those nodes. Every other node having a 0 weight connected to it, where those nodes have a high weight. And thus, you can figure out when you have a 4 in there. Does that make sense to everyone? That's sort of clicking? Yeah.
So are those nodes manually set to begin with, or are they randomly?
Randomly, and then through this back propagation process, feed forward, back propagate, these weights are optimized.
So what you would probably see is just a bunch of random white and black pixels that would eventually maybe get narrowed down.
Narrowed down to a region. Yes, exactly. Like if we were mapping out the connections between this first node and this first hidden layer, at first it would just be like this gray sort of static looking thing. And then as it optimized, it would become something like this, where it actually serves a purpose, essentially, in the network. Yeah? And then via the combinations of those nodes, you can get something like a 6, or a 7, or a 9. Does that sort of make sense to everyone? Cool. Awesome. All right. And you have these hyperparameters, and that's essentially the decisions you make as a data scientist or whatever you want to call it. It's basically your hyperparameters in this case would be how many nodes are in your first hidden layer, how many nodes are in your second hidden layer, how many hidden layers you have, the type of activation function you use, whether you use biases or not, those sorts of choices that you make, because you can't really control, oh, and also learning rate, which is essentially how big of a step do you take downward for gradient descent. And these are choices that you make, but you can't really, aside from changing those hyperparameters, change how it learns. Like, it will just go through the process of backpropagation to learn. Okay. The next thing, convolutional neural networks. Now, things are going to get even more abstract for this, and I hope I can relay this. It's used for spatial data. And what I mean when I say spatial data is I mean data that if you switch around the rows or columns, it no longer retains its meaning. So that cancer data, you could switch around the column for, I don't know, lump thickness and sickle cell, whatever, and it would still retain its basic meaning. But an image, for instance, you can't just switch around the rows or the columns and have it still retain that meaning. So that's what I mean when I say spatial data, where position is important, something like an MRI or an image. Anyway, so what convolution does is it does this feature learning. And we're going to use an example to sort of relay this idea. And stick with me here. So let's say we're trying to create a model that can identify when we have an X in this 5 by 5 matrix. 2, 3, 4. So let's say the X is something like this, where the colored in pixels, if you will, are represented by 1s, and the blank pixels are 0s. The whole idea of convolution is you take what's called a filter and you slide it across your image. And a filter in this case might be something like this. It might be a 3 by 3, so let's there, filters. Or something like this, an optimized filter. Again, it would start completely randomly and it uses backpropagation to create these optimized filters. But one would probably be something like this. And what you do is you slide this filter across this image, starting from the top left. You can see, for this first block of the slide, it matches up exactly. So your activation for your filter map, and I'll get into what that means, for that section would be a 1. It'd be a completely activated, because every pixel that's activated in the filter is activated there. Now, when you slide it over 1 and you do it again, you'll notice there's no pixels activated, so it'd be a 0 here. You slide it over again, you have 1 pixel there, I think that's activated, so it'd be something low, like 0.2 or something like that. And then you keep going down, and you hit a high activation here, and you hit a high activation here, you hit another like semi-activation here, so it'd be something like this. 1, 0, 0, 0, 1. And that may be too small for everyone to see. I hope it's not. But essentially, high activations along this diagonal, where you can see it matches up with the pixels in the image. Another filter might be something like this. An X. And you can see, you can slide it across this image, and it may get some small activations here and there, but where it's going to get its highest activation is right here in the center. And so it's going to look like something like this. Let's give you like 0.2, 0, 0.2, 2, 0, 1, 0, 0.2, and 0. Something like that, where you can look at this filter map from sliding it across this image. You can see it has highest activation right in the center. And when you stack these filter maps on top of each other, you get what's called a filter stack. And you can see what I've done here is I've taken an image and I've reduced it into sort of representations of activations of these filters. And that's what, when you see this two-dimensional image, oh shit, I should get that away from that TV, these two-dimensional images that come into this block, what that is a filter stack. It's a stack of these filter maps. And then you use pooling, which basically just reduces your data. I don't want to go into like what that is. I can tell you later if you're interested. And you basically just do that over and over again. And basically you get filter maps of filter maps via doing it over and over again. And then at the end you use a fully connected layer. You basically take the top left of your first filter map. in your filter stack, and you just list them out one by one until you get to your last filter map in your filter stack, and then that's your input for your fully connected layer. Now questions, I'm sure we have some.
Where are the filters generated?
The filters are generated the same way that the weights are generated. They're completely random at first. You can imagine them as static, and they're optimized through backpropagation. Filters would not start off looking this clean. They would start off, being just like sort of staticky. And then through this process of backpropagation, which really only utilizes basic calculus, like derivatives and chain rule, for any of you who know basic calculus, and via that you can optimize these weights in this case. Yeah. Any other questions? No? You sure? All right. So what the convolution does is your feature learning. Let me get my fancy stick back. And what the fully connected at the end does is the actual classification, because we know it's good at that. All right. All right. If you guys don't want to ask questions, I'm going to assume you perfectly understand what I'm talking about. But yeah. All right. So here's some things you can do with a convolutional neural network. Dog or mop? Is it a mop or a dog? So what a convolutional network's filter might look for when identifying a dog is have one of these filters that has is basically a dark spot in the center. And it would look for this little puggy little nose sticking out. And via sliding that across the image, doesn't matter where that puggy little nose is sticking out, it'll say, hey, there's a puggy nose. This is probably a dog, not a mop. Does that make sense? Does that sort of click with everyone?
So when you're building a model, you'd have to feed it only dog pictures?
No, you feed it both. And via that process, it would identify that where it finds this dark black spot, that is associated with the dog images. When it's not present, it's mouse. Does that make sense?
Are you feeding it the classifications with those?
Yes, yes. This is supervised machine learning. So every time you're giving it the label or the class. And you can imagine the filters for like a complex image like this. Your first filters are something like this that represents sort of edges. So this one would get activated when there's sort of an edge that looks like that. This one would get activated with an edge that looks like that. This would be like what was used for the pug nose right there would be like the filter that you slide across. And I've sort of neglected to mention this, but the beauty of neural networks and what I find so intriguing about them is that we don't fully understand them. And that's something that you really can't say about almost anything else in computer science or related. We don't know what these middle convolutional layers really represent, or in a deep neural network, what they actually represent. Or going back to that first deep neural network problem where we're trying to classify handwritten digits, we imagine that each node represents a region being activated, but yet you can do something like add 3 nodes or take away 5 nodes from a hidden layer, and it'll still do the job of figuring out what, it may not do it quite as well, but it can still figure out a way, a perfect alignment of those weights to do the job. And especially in very deep neural networks where there's several hidden layers, something like a convolutional neural network, we don't really know what those middle layers actually represent most of the time. It is sort of a mystical forest in a concrete metropolitan that we're used to as programmers. And it is, when you get into it, it is seriously fascinating. Because it can, not only can it do things like this, things that you may even struggle with at a glance, telling whether that's a dog or a mop or not, but through these processes, it can do incredible things. And I'll show you some sort of piece of candy examples of this a little bit later. But yeah, there's the hyperparameters. We won't go through this, but these are the choices that you make as a developer or as a data scientist when you're setting up one of these. The number of features that you want to have, your padding, which is just you put some zero value paddings right here so that the center of the filter can actually see the edges. And your stride, how much you shift every time when you go to your next, point in your feature map. And for pooling, same sort of thing. We didn't really go over pooling, just data reduction algorithm. That's essentially all it is. And then your fully connected layer at the end of a convolutional layer, you have the same choices, the same hyperparameters that we went over for deep neural networks. Now, I think we're getting into some cool stuff. deconvolution, applying deconvolution to a convolutional neural network. You can do some pretty cool things like this. You can take an image, you can apply convolution to it with, all you have to do is change, tweak a little thing where when you reduce your data, you take an index of where, you just add a little piece, a very small piece, so that you keep your position data essentially. And you apply convolution to it, and then you apply deconvolution, which is essentially where you take and you repaint those filters back onto the image via the filter maps inside the filter stack. Does that kind of make sense? You're essentially repainting with those filters that you've created through convolution. And what you can do is, for this example, you apply convolution, you get it down to those high-level features, and then you apply deconvolution using the same filter set and the same filter maps. And then at the last layer before your image layer, you would take your low-level filters from this image and you just swap them out. And via that, you can sort of create this image with all of its high-level features in place. You can see these houses are still there, this river is still here, but the low-level features are from this image. And you just sort of, it's kind of like you quite literally paint an image with another image. Does that make sense? And I think it's pretty cool. I don't know about you guys. Like, I think that's really, really awesome. And yeah, we'll go into some coding examples, and during these I'll tell you about, now from what you guys have learned already, I will sort of go on with some other concepts that you now probably will be able to understand with your current understanding. Assuming you've paid attention and haven't fallen asleep yet. Yes?
Does it decide the size of the filters?
No, you do.
Same?
That's a hyperparameter.
Okay.
Like, yeah, you decide your size of your filters. It'll optimize those filters, but you can only pick this size, essentially. Now, here's an example. Oh, my God. One second. Because I'm clicking on my wrong thing. All right. Give me that. Now, what this is a convolutional neural network where you can draw a digit or a letter, and it'll use a convolutional neural network. It'll feed forward through a previously optimized network, and it'll guess what you just wrote. Now, this is going to be, this is going to be hard. All right, so let's say 7. Try that out. Come on, girl. Yeah. Let's try, I'm pretty sure this thing doesn't do so hot on 8s, but we'll try an 8. Come on, 8. We can try T. Submit. Now, sort of the things I've been drawing on here so far are things that probably a fully connected neural network could figure out. However, here's why a convolutional neural network and using it for this case is so cool. Is because it doesn't matter what position, it looks for a pattern of features. So you can write a smaller 7 over, oh my God, that's not going to work.
Well, clear.
All right, we'll see if this works. You could write a smaller 7 there, and it'll probably figure out that it's a 7. And you can write a 7 over here, and it'll still be able to figure out that that's a 7. You can write, a 7 up here in the middle, and it'll still be able to figure that out. And if this is a fully connected network, it would not be able to do this because, remember, the first hidden layer is essentially regions of activation. So every time you'd have to draw that letter the same size for it to be able to effectively classify it. Whereas a convolutional neural network, because it's sliding those filters across and finding these patterns, it doesn't matter where that 7's at. So I think that's pretty cool. But here's also a pretty neat thing. And what this is let's play Flappy Birds with a machine learning model. And essentially, this model has 2 inputs: the distance between the next gate and the height between the center of the gate. And for those of you who aren't familiar, Flappy Birds is a game where you basically click to flap or to raise your bird up, and you try and get it through these little gates. It's just a little simple arcade style game. And all this network consists of is 2 input nodes, that I just mentioned, 6 hidden nodes. So this is not a deep neural network, and then 1 output, which is essentially to flap or not to flap. This is essentially what it decides. And what this uses is called the genetic algorithm, where it's a different approach to optimizing your weights, where instead of using backpropagation, what you do is you create several different models. with randomized weights, you see how well those models perform, and then you take the ones that perform the best, you create sort of mutations or variations of those sort of combination of weights, and you try it again. You keep doing that. It sort of works quite like evolution works. All right. So here's what that looks like. Come on, girl. So yeah, you see, it starts with some of these get done, but the one that gets the furthest is the one that's copied and mutated. And through that process, it's sort of an alternative to backpropagation. You can optimize a neural network. Kind of cool. Here's something that's a little bit cooler. Now, what this uses is a recurrent neural network. And what a recurrent neural network does is essentially in its input, it keeps in mind, its input includes its output of its previous output, essentially. And you use this in sequential data. Let's take a video, for example. You'd probably use the convolutional network to analyze each image in the video, and then you use a recurrent neural network to analyze the sequence of events. Imagine trying to figure out what a guy's doing. He's currently unloading a car. And so he walks to the car without a box, he grabs the box, he has a box in his hand. Well, a convolutional neural network would have no way of knowing sort of if he's loading or unloading the car. But via a recurrent neural network that takes in the input of the last output, and using sort of long short-term memory is the term for it. I'm not going to go into what that is, but it can also take into account the output of several iterations back. It can determine that no, he's not unloading the car, he's loading, essentially. Does that make sense? Okay, cool. So what this guy did is he trained a neural network, a recurrent neural network, to imitate how he plays Mario Kart.
3 of these cards are being driven by a recurrent neural network I call Mario.
And one's by a person, essentially. I'm just going to mute this. Anyway, but yeah, so one's being driven by a person. And so he trained this on basically video of him playing. And as you can see, it performs very well. Like, it can win championships in Mario Kart, which is pretty fascinating. One of the things he had to do in this is because he's training it with video of him playing and not giving it some reward mechanism, all it knows how to do is mimic his driving. So it doesn't know when it's doing well. It just attempts to drive like he drove in the training data. And what he had to do for this is, he would give it all this data from his original training data that he created. But then he would realize that it would get backwards or something like that. And because he doesn't drive backwards, or he doesn't get into that situation a lot, it doesn't know how to correct for that. So what he had to do is he had to let it run until it got into one of those weird situations. And then he would take back control, recording the data for training purposes, like to train the network with. And so he would teach it how to correct those mistakes that it would make, essentially. Any questions? And also, this is another, just a sort of a set of games, essentially. And you can say it's classifying the best move to make. And this would be using a fully connected network because you need to know the position on the screen of where it's at. So, depending on the situation, you want to use different types of networks. And essentially, that's it, guys. I hope this was interesting. Again, the source code for the examples, the PowerPoint, the resources I used, and as well as a video of this presentation are all going to be on SharePoint, shared directory, events, lunch and learns, Josh Bedlow Lunch and Learn. And I hope you learned something. Appreciate you guys all sticking through that. I know it's...
Josh, I've got a couple questions.
Sure, yeah.
So, neural nets can be computed system.
Yes, oh,
So,
thank you for making that point. Yes, I meant to go over this, actually.
so why, and Python is not one of those efficient languages for us to use. Why is Python so popular?
Because you have tools like TensorFlow. And what TensorFlow does is, you guys may know, Python sort of executes line by line, but what TensorFlow does is it allows you to create what they call a graph of all the sort of computations that are happening. And instead of executing line by line the way that Python normally does, and which is sort of an inefficient, or, sort of slow way of doing things. It compiles this big graph, and then it executes it all. And I think it doesn't use C or something like that. It may use a different language for efficiency or something like that. But essentially lets you use Python with efficiency, essentially, with computational efficiency. And also, you mentioned something which I meant to mention as well, which is sort of that neural networks are computationally expensive. And that's why it wasn't until the past couple of years that they've actually become popular, because we have tools like AWS where you can rent a supercomputer for a few dollars an hour, and so you can have something that can handle these huge amounts of memory. Because let's consider a fully connected network real quick with an image that's a 1080p image. So you have 1,000 by, let's say, 500, just for nice round numbers. So now you have 500,000 input vector, or input array rather. That's a lot of weights, especially if you have a few hundred nodes in your first hidden layer. You can imagine that's a huge number, and that's why it's really been not the go-to network, or the go-to machine learning model for machine learning. Support vector machines are much faster because it's just a binary classifier. You give it new data, and it can use those hyperplanes to classify it almost instantly. Hope that makes sense. Any other questions?
Yeah, the most important question, where'd you get the cool pointer?
I made it, yes. I thought you would not appreciate me pointing a laser pointer at your new TV. So I went to Marshall's, and they had these little cones and these dowels, and I was like, well, this kind of looks like a vector, so I think I'll use it. But yeah, any other?
What are your thoughts on using like a graphics processor?
You want to use a graphics processor. CPU is pretty inefficient for these type of things. When you get into the more advanced models, they typically tell you to switch over to a GPU, because otherwise you're going to be waiting days for these models to optimize. And ideally, you want to be using TPUs, which is like a server-like processing, essentially. Any others?
Interesting scenario.
Yeah, sure, let's go.
If you were to design the neural network to predict prime numbers, how would you go about it?
Your input would be a set of all numbers, and then your output would be whether it's a prime number or not, essentially.
I couldn't really say what the best way to do it would be.
I wouldn't know either. Your input would be size 10 array. Also, something to bear in mind with all of these models is that you need to give it numerical data. Like, you can't, give it man or woman. You got to give it a 1 or 2. And one of the files that I'm going to include in this is a tool for sort of factorizing your data. So turning man to 1, woman to 2, turning cat to 1, dog to 2, that sort of thing. But what you would actually be feeding it for your input in that sort of scenario, where you're trying to tell it, you would basically, I forget how this would work, but like, let's say we're trying to represent a number as a byte. And it's been forever since I've done this, but but it would be a vector, like, let's say, I'm pretty sure 2 is like a 0, 1, 0, 0, blah, blah, blah. You'd give it something like that. You probably wouldn't give it the number. You'd probably give it like a 1 hot vector or a mini hot vector, or array rather, which if you guys aren't familiar with, it's just basically an array where one or more value is sort of turned on as a 1 and the rest are zeros. I realize that's probably unnecessary information there.
So you would give it a binary input of like the previous number, and then you would train it to give the output as a binary output of the next number.
I'm not sure I understand. No, you would just give it like, you could just feed it the number. In fact, you could feed it, whatever number it is, and your output would be a binary. It would be either 0 for no and 1 for yes, essentially, as a prime.
Right, but like, really the only information you have with prime numbers is the previous prime numbers. So
Yeah, I see what you mean. I don't know. I'd have to think more on that, I think. Like, but initial broad stroke approach would be just feed your input either as a byte representation, like, or just the number itself, and give it decently sized hidden layers and let it try and optimize. Maybe it'll find a pattern, maybe it won't.
I
Essentially,
mean, I just assumed that they were taking it away.
yeah, well, these things can do surprisingly complex tasks. Like, but I don't know. I'm not sure the answer to that. You could try.
I've been considering it, but I didn't really know enough about neural networks to really give it a try.
Yeah, and also that reminds me of something like which again I mentioned that I'm gonna have that example code up on SharePoint. That code, you can utilize that code into any model you want. All you literally need to do is change which columns you drop, which meaningless columns you want to drop. You know, change your file path so that it points to your file, and essentially change what is your label column and assign that to the sort of the label values, and you can use that exact code. I have my permission. I think I copied it for someone else anyway. Like, but you know, you can use that code that I gave you to create a machine learning model very quickly. And also, I'm going to include other code that includes neural network examples, and you can use something like that to test your theory. You know, what I mean, create a neural network that attempts to find prime numbers. Anything else?
What kind of stuff do you use it to apply to?
I have applied it to sentiment analysis, which essentially the input is you give it a sentence, and it tries to tell you whether it's a positive or a negative sentence. So essentially, you know, you give it, "I hate cookies." It'll tell you that's a negative sentiment to that. And the way you train it is you give it a whole bunch of examples. And this MNIST data set, that MNIST library that I mentioned, has a data set for this. And basically it's just thousands and thousands of examples of positive and negative sentences with labels for each one. So you use supervised learning, and you can use a neural network to attempt to classify the sentiment, I guess.
Actually this morning happened to see something interesting about, they took predictive text and basically wrote a Harry Potter chapter.
Mm-hmm.
And it was surprisingly accurate. I just thought it was kind of funny that on the same day that we...
Yeah, exactly. And to do that, you would use probably a fully connected recurrent neural network because language is sequential. You use recurrent for sequential data, convolutional for spatial data, and fully connected is sort of used with both of those. It's sort of the does it all sort of thing. You kind of use it for every application at some stage. But yeah, you use a recurrent neural network to do that. Yes?
But if you wanted to take like a huge list of stuff and then narrow that list down using a neural network, but still like return a list. Like if you were to filter a list based on some criteria, but
Wouldn't that be the same as categorizing it?
yeah, or like creating a lexicon or something like that, where you contain all your words that are present in each file. Like, I'm not sure.
I mean, I guess the main point is how would you return multiple things? Because it seems like most of these just return like one.
Yes, you have to, for everything you return, it has to be the same size. And that's where something like a lexicon comes into use. I don't know if you guys are familiar with what a lexicon is, but like let's say you create a lexicon for a sentence. I am Josh, there would be an index, there basically is an array where each index represents a word present in the text, where I would be the first one, Ann would be the second, Josh would be the third, Medlin would be the fourth, period would be one, and then I like cookies. That I would not be another index in that lexicon. It would be just that first index. So it's basically like kind of a dictionary, not how you normally think of a dictionary, but sort of a dictionary of all your present words, essentially. And via a lexicon, you can output, you know, sort of the words that are present in a text. If you have a lexicon of all the words that are present in all of the text, you can represent data that sort of isn't the same size, but because you're using this lexicon, it is all the same size. You can use one of these models or a neural network. I hope that makes sense.
Yeah, I mean, I'm not.
If you're talking about multiple outputs, I mean, just like super simple, even in like the Flappy Bird example, there's like, you know, kind of just a...
Right, but that has a defined number of outputs.
Right. So you're talking
Whereas,
about
like if you're like
variable
filtering
output
lists,
number.
Yeah, it'd be variable
Yeah.
output.
Sure.
I think,
Okay.
So I guess neural network really wouldn't apply for something like
I'm not sure I even understand the question, so I like, when you say multiple outputs, what do you mean? Like, what would be an
that.
example?
Like if you wanted to give suggestions based on a big set of data, but you don't know how many suggestions, like,
Yeah, exactly. A lexicon would be perfect for that, because you could have all your possible, the output would be an array of all your possible suggestions, and then you would just have.
a
Yeah.
number for each.
Yeah, exactly. You'd have a one or more value for your strong suggestions, and then everything else would be a 0.
Okay, and then you just have to go through a list and manually pull them out.
Yeah, exactly. Anything else?
When deciding your weights, which way is better? Doing it the way they did the Flappy Birds, or doing the local minimums? with the derivatives?
I say generally speaking, using gradient descent and backpropagation is probably the best way, especially for huge problems that require a lot of computation. The genetic algorithm is effective, like it can optimize a network, but it's sort of a bit of an inefficient approach, but it looks really cool when you apply it to something like a game, because you can watch it actually work. So I wouldn't say it's, a novelty necessarily, because it can be effective, but I'd say it's highly effective when you want a novelty. But yeah. Any other questions?
And in choosing because do you choose the size of the step down whenever you're doing the finding the local minimums?
Yes, that's your learning rate that you specify. Yes, exactly.
So-
for gradient descent, that's a hyperparameter for your neural network.
Can you change that on the fly?
You can't change it, in the middle of training, but you can change it, train your network, change it again, try and retrain the network from scratch, that sort of thing.
Okay.
What happens if you overstep?
You can imagine, let's say, a situation like this, and here's a steep local minimum, and say you're stepping this big. So every time you're stepping, you never actually reach that local minimum. That would be a situation like that. Anything else? All right, well, any questions, come ask me later. I'm not an expert on this stuff, but I do have a decent knowledge of it. And this stuff gets me excited. I hope I relayed sort of the coolness of this. I know it was a long presentation, but this stuff is, again, it's sort of like a mystical forest in this concrete jungle that we're used to. And I think it's really neat, and I hope you guys do too. But yeah.